So this picture is, these pictures are from Mexico, from a place called Puebla. Puebla is a town close to Mexico City. It is a UN World Heritage City, which has lots of history behind it. So this picture that you see on the top, they claim this is the oldest pyramid, like the pyramids in Egypt. So they said this older than that, which is situated close to Puebla. And on the left one is just an old building from I don't know, centuries, maybe 2 centuries ago. All right, so we were talking about Bio-Nano design last time, and especially we were discussing, okay, what do we want to study? What kind of interactions we want to measure? So we may be looking at a single molecule that we want to measure, and those single molecule would include maybe organic molecules, peptides, synthetic polymers. It can be enzymes, antibody receptors, a whole bunch of things that can give us a state of a living system. It can be a complex of molecules which we may be interested, which would mean that it can be organelles from a cell, or maybe it can be the whole cell we are interested in, right? So of course, a mammalian cell or bacterium or even yeast cell, which would again, a culture of those cells can tell us the state of these sample or where we get the sample from. It may be a bunch of samples, right? For example, we take a sample of a tissue in biopsy. So we may be looking at a biopsy sample for that matter. So now in all those cases, the recognition occurs at a molecular level. And that's what we want to employ a nanosensor. So we can look at those molecular scale reactions to see if a target entity exists or not. Now, in many cases, so in all cases, we have this recognition element, right? Which can be the opposite of all these molecules that we are looking, which we would know from reactions in test tubes, that they have specific binding. Now, once that binding occurs, we have to transduce that signal. Now, that transduction can happen at first level. There can be maybe a change in the chemical, which would be oxidation, for example. It may be a change in the chemical nature. Maybe there is a reaction that occurs, and there is a byproduct of that reaction. The change can be because of the binding, there is a change in the overall weight. Now, this weight change would be very small, right? But by picogram, or even smaller than that. But there will be a change. It can be a change in the optical properties of the surface, or maybe the molecules, fluorescence, for example. There are photoacoustic changes. Acoustic meaning the sound that may be coming from it, or maybe the sound gets damped from it. So whichever the case. There may be a reaction which is exothermics, which means there is a heat that may be produced. So these are all different ways how there can be a transduction. Now, for each of these changes, there is a relevant detection modality that we have, or we have developed. For example, for chemical substances, we may be looking at change in the potential at the interface because of oxidation, because of addition or removal of an electron. If we are talking about weight, we have this approach which is called Quartz crystal microbalance. So the idea is that we have a crystal which has a resonant frequency. So when there is a very minute change, that frequency would shift. And that we have done calibration beforehand. So we know that what kind of shift is related to what kind of very, very, very tiny minute change in the weight. There's cantilevers which have been used to detect those small changes in weight. Now, if there is a light interaction, we have photomultipliers. We have photodiodes that can look for those emission of light, or maybe change in light. Maybe there was our design of a molecule had a photo emitter molecule and a quencher next to it, which would absorb that light. And when there's a reaction, they go apart, which would now result the photon coming out. And we can detect that with photodetectors. Similar way, for heat, we can have thermistors, which can detect very small change in term of change of resistance. So these are various ways how we can detect these the analyte recognition, and that signal transduction can be then recorded in either as an electrical signal as a display, or maybe we measure the light. Maybe we take an image and then we take the fluorescence count on that image. So there are all these different ways how we can detect, how we can transduce that signal. Now, if we talk about electrical signal, there are a bunch of ways, right? So in amperometric biosensors, it can be potentiometric, which is there's a potential at zero current. So there's no current, but we measure the potential. Or amperometric, which would mean we have applied a specific voltage and the current changes at that specific voltage. There is redox, which we talked before. Redox is reduction oxidation. And I remember it by a mnemonic, right? Where loss of electron is oxidation, LEO, L-E-O. Leo is, if you know stars, Leo is tiger, right? Leo, the lion, says Gur, G-E-R. So one of my professors told us how to remember this. LEO, loss of electron is oxidation. GER, gain of electron is reduction. So that electron exchange would result into the change in the current. So when a molecule is reduced, then which is gain of electron, it has now more electrons than the oxidized form, right? So now the reduced form can donate an electron. So you will see like current flowing. And the oxidized form can accept an electron. So then you will see the current flowing in the other direction. So that's how we would see electrically how the signal comes, which gives us an idea that that reaction occurred, or that that particular thing happened, the molecular recognition took place. The other type, the optical, which is generally called image processing for engineers, it has to deal with looking at lambda, looking at photons at specific wavelengths. So there are a bunch of ways it may happen. Fluorescence is a way where there's interaction with light and a molecule would emit photon. Absorption would be where you would strike a light and the molecule would absorb that particular wavelength. And on the other side, you would have detector, which means if you throw a particular wavelength and you don't get that wavelength on the other side, which means your molecule has absorbed that photon. And you would know for that particular wavelength what kind of reaction occurred. So now we excite a molecular complex with a particular wavelength, like quantum dot, and then in return we get an emission. So the lambda of excitation may be different from the lambda of emission. So we would know what is our design of experiment and what to expect from there. There may be change in intensity that we would measure, which means the number of photons that are emitted. There may be change in absorption that we would measure, which would again mean number of photons which pass through and get to the other side of the sample to the detector. There may be change in wavelengths of the emission, which means you have excited and then emission happens after the interaction. That change in wavelength can be something that we can measure. There can be change in the fluorescence lifetime, which is that you strike, you excite it, and then there is some kinetics of emission which happens after the absorption. So there is some time delay. So that lifetime change can be used as a detection modality in that case. So now there are some molecules which exist in living entities which emit light. Right? So we know what you call jugno, right? Uh, it emits light, bioluminescence. So that chemical has been isolated. It is used in experiments. The bioluminescence is the production and emission of the light by a living organism. And it happens because of chemical reactions during which the chemical energy is converted into a photon, and that shows up as an emitted light. So those bioluminescence is used as well, which is part of that reaction of recognition in that sensor. The signal of light, very more recently, last 2 decades, is a new phenomenon called surface plasmon resonance, which is more in the physical property of light. So these are surface plasmons are the changes in the, so we strike a light onto a hard material. So there is a fluctuation in the electron density at the boundary of two materials. So that's occurring because of the energy of that light. So light, in a say, we say the light gets absorbed or light gets trapped on the surface, which is the light gets translated or transferred into the change in the electron density of the material at the surface. So the surface plasmons are surface electromagnetic waves that then travel along the metal and dielectric surface, so metal and vacuum surface, right? So we are striking the light through the vacuum. So they get trapped at the surface and they travel along the surface. Now, this wave that's traveling, it's along the boundary of the detector surface or the surface where molecular recognition is happening. So can be metal, can be semiconductor, whatever, or glass even. So it's happening at the interface of that hard surface or the vacuum or air or liquid maybe. So their oscillations are then sensitive to the change at the boundary, which means the recognition would be readily measured or seen by the changes in the surface plasmon. Now, the excitation of the surface plasmons with light is measured in the form of surface plasmon resonance. So there is a specific energy transfer that occurs, and change in that would be indicative of the binding event that we are interested in. We many times look at the cell itself over a long period of time, and we see if the cell internal operation gets disrupted and even cell deaths if that occurs. So these are a few ways of transduction that we use a lot more when we deal with nanobiosensors. Or we employ these kind of sensors to see the changes at the interface of nano and bio. Right, so I thought we can go a little bit more in detail to have a closure to that. Yeah, questions?
Sir, his bioluminescence are harmful to humans, sir?
Say it again.
Sir, is bioluminescence are harmful to humans, sir?
I didn't quite get the question. Is the bioluminescence?
Yes, sir.
It's like the many living organisms, they emit light, right? So the simple example is firefly, what you call jugno.
Mm-hmm.
You know jugno? in summertime and in grassy areas we see those small. So that chemical is a fantastic example of bioluminescence. So these are the luminescence or the chemical reactions that result into the chemical energy change emits as the difference of energy before and after reaction as a photon. And there are many other organisms. There is fish. There is we know specific proteins which are which give luminescence can be employed as indicator of the reaction or the binding event. Yeah, Habib, go ahead.
Sir,
Habib.
can you re-explain the concept of surface plasma? You said
Surface
something
plasma.
like surface is a surface electromagnetic waves. Can you re-explain that, sir?
Right. So I'm talking about what is called, let me write it down, SPR, or surface plasma resonance. Right? And R is for resonance, but surface plasma. So these are, so in some materials, when you strike a light, so some of the light which gets, so light has two waves, right? E and M. So some of the waves, they start traveling at the interface of the hard surface and the mediums, two mediums, right? So one is, in our case, it can be metal and dielectric. It can be metal and vacuum. It can be metal and liquid. Now, these lights, they travel along the surface. So you can think of that light gets trapped at the surface, at the interface of those two mediums. Now, if there is any change in that surface, that can disrupt those, and that can change the resonance of the surface plasma. Now, at the interface is our recognition element. So if the binding occurs between recognition element and the target, that can result into change of surface plasma resonance. So now if you are go into more physics of surface plasmas, that's a whole different area. But to break it in very simple terms, the idea is that the EM wave, which results because of the the striking of photon on a surface, that is traveling, and that's an EM wave. The fluctuation in that EM can be measured, and that would happen because of very, very small, simple changes on the surface. On that surface, we can put down our recognition element and ultimately carry out the target recognition, which is the basic idea of a Bio-Nano sensor, right? All right, questions? I see a chat question. All right, so that's due till today, like the last. Oh, so today was the presentation. So how do we do? Okay, I have one team who has already sent me the presentation, and we'll get to that.